All right, let's go ahead and get back into it. So we left off this example yesterday. We're trying to figure out if 1, 1, 1 is in the span of these three vectors. So let's remind ourselves, what does it mean? What's the span of three vectors? What does that mean? The span of a set of vectors. Go ahead. Right. So it's basically all the linear combinations of those three vectors. So now I want to know is 1, 1, 1 among those vectors? So basically, is 1, 1, 1 a linear combination of these three vectors? So we started looking for that yesterday, right? So how did we set that up? Right. So basically, we can put this as an basically what we're looking for is, if I can add some multiple of the first vector plus some multiple of the second vector plus some multiple of the third vector together, will it make 1, 1, 1? So here's the equation that we're basically trying to solve. So I think we tried something yesterday and it didn't work. So what was it yesterday that failed? What's that? So we couldn't find an inverse, right? So that doesn't like conclusively tell us that 1, 1, 1 is not in the span, because there are cases where maybe there's an infinite number of ways that we can combine C1 or that we can combine these three vectors to get 1, 1, 1. So the inverse did not really pan out for us, but what we can do is this. Let's try to reduce this matrix, not so we're looking for an inverse, but now let's just look for a solution to this. Now we know if this works, it won't be unique, because if there was a unique solution, we would have found the inverse. But let's try to solve this thing. So how can we do that? How can we start trying to find a solution to this? Gaussian elimination. So we can try to go for that upper triangular form. If we get there, then we can probably do the rest. So how can we start? So we're looking for Gaussian elimination. We're looking for upper triangular form. What should our targets be? Like, what should we be trying to change? Right. So basically, our goal is going to be this essentially. So I don't know what's going on up here, but below this diagonal, I need to have some zeros. So that's what we're marching toward. So now how can we make that happen? 2 plus 2 of R3 plus R2 back to R2. So I believe that'll give us one of the zeros we want. So 1, 4, 2, 1, 0, 3, 3, and 3 again. 2 times row 3 plus row 2. Okay. And then 1, 2, 0, 1. Good. What's next? Okay. Subtract row 1 minus row 3. So 1, 4, 2, 1. Row 1 minus row 3 gives 0, 2, 2, 0. Okay, so kind of already see the problem we were going to see yesterday. This is a problem for us. For the thing we're trying to solve, do we know yet if this is a problem for us? If you're not sure, let's keep going. All right, so what else can we do? Go ahead, Jack. Row 1 minus row 3. And put that where? Row 1. What are you trying to do with this? Okay. We actually don't need zeros above. So we're just like, let's just try to go for trying to get the upper triangular form. So in that case, the only thing we have left to do is make that a 0. I see a couple ways that could make this easier. I can scale row 2 and row 3. So I'm going to put 1/3 of row 2 back to row 2. And I'll put half of row 3 back to row 3. So I get 0, 1, 1, 1, 0, 1, 1, 0. Any red flags going off yet? Why? I suspect you're right. Also, what do the bottom 2 lines of that matrix say? I don't think that's possible. If you just add them together, they can't equal 2 different numbers. So I have a suspicion that we just answered this question, but I think if we do this subtraction, we'll be absolutely sure. So row 2 minus 3, put that back to row 3. 1, 4, 2, 1, 0, 1, 1, 1, 0, 0, 0. 1. Yeah. Problem? I think the way I did it should be positive. It doesn't really matter. Yeah, if you subtracted R3 minus R2, then yeah, it should be negative. Either way, I think we have proof, right? That there is no way that I could combine these 3 vectors to make 1, 1, 1. Found no possible way that happens. Any questions on that? All right, let's give another vector. How about 5, 4, 1? How could we find out if 5, 4, 1 is in this span? Could do Gaussian elimination, right? I'm so glad you brought that up. I don't want to go through all that again, right? So the thing I'm going to do Gaussian elimination on is this. Except on the right of this line would be 5, 4, 1. But if I start doing all the same steps, I think everything on the left should be the same, right? On the right will be different. But if nothing else, I think we made like a recipe for it, right? So let's do this. I know 142,011. I know that I can make the left-hand side of this look like this, right? So then all that matters is, actually, we're not guaranteed to get 541 from this, right? So we could reduce it down to that, but it's all going to be a function of what do we want out? Like, we want to get 541 out of this, right? Or would you take the same steps that you would have anyway? So let's think about this. When we do Gaussian elimination, does it matter what's on the left-hand side of that line? Does it matter what's on the right-hand side of that line? We don't even look at it. So we have to like adjust it, but none of our decisions, I don't think, come from what's on the right-hand side of that line. So I think this is our goal. That our thing already I forgot. 142,011. 011 000. But now how do we figure out what goes on the right-hand side here? Would it be okay if I just did some revisionist history here? Let's just do everything we just did and with our new solution. So I'm going to blank all these out. These slides will be useless to look at later, but the video will be helpful. So now I wrote down all the steps we took. So 2 row 3 plus row 2. So 2 times 1 plus row 2. 561. All right, and then row 1 minus row 3 back to row 3. 564. And then what did I do? I cut row 2. I took a third of row 2, 2, half of row 3. Ooh, what does that tell you? Does that change our opinions or anything yet? I'm gonna go ahead and cross that out. I'm already feeling optimistic. So then what's the rest that's gonna look like? Row 2 minus row 3, 5, 2, 0. So now that we're looking for 5, 4, 1 in the span of these three vectors, what did we find out? Does it work? Does it exist there? It exists. So is 5, 4, 1 in the span of S? Yes. Okay, if we're saying yes, then we should be able to talk about what combination makes it happen. So what combination makes it happen? Does it end up just being 5 of the first plus 2 of the second? I don't think it does. So we can't get any more information than that, but for now we can say yes, this does exist in the span. We were able to find that C1, C2, and C3 would have existed. Actually, there's an infinite number of ways this happens. So what did we learn from this matrix, this final matrix we have here? So what do we know about the values of C1, C2, and C3?
C1 equals 5 minus 6.
5, 1, so 5 minus 4 C2 minus 2c3, and c2 equals,
minus.
I think it's just 2 minus c3. And then c3 is a free parameter. So like we suggested last time, there is no one way to get, there is no one triplet of C1, C2, and C3 that makes 540 happen. But you can pick whatever C3 you want. So let's say C3 is 0, C2 is 2. That would make C1 negative 3, I think. If I did my math correctly, that's one possible way to do this. Negative 3, 2, 0. So if I take negative 3 of the first vector, 2 of the second one, and I leave the third one off entirely, I'll get 540. How are we doing so far? So we found, or 541, not 540. So we found that we proved that one vector does not exist in the span. We proved another vector does. Can we describe all the members of this span? There's an infinite number of them, so if we're going to describe them, we have to be careful about how we do it. Can we talk about what the span of this thing looks like?
This is something like all real numbers except when are all ones.
That's basically you've only left out one vector then. So clearly 1, 1, 1 is not in there, but there are probably others that aren't. So now we're kind of going the opposite way. Now I'm not giving you a vector. Now I'm saying, here are the vectors. What are all the vectors? Or like describe all the vectors that can go in here. So now I'm solving this equation in a more arbitrary way. So if I multiply this matrix by some collection of constants, C1, C2, C3, I want to know what's going to come out of it. So I don't know, ABC. So here's my goal. I want to say the span of S is equal to the set of vectors that look like ABC. But I already know that ABC can't be whatever I want. I have to have some kind of restrictions on them. How can I figure out what kind of restrictions go on them?
You just multiply your matrix by 663.
I could. Then I would get 3 really complicated equations, right? That would totally work. What if I were to reduce this matrix a little bit and then solve for C1, C2, and C3? Does that sound a little bit redundant? It should, because we just did that. I have a family of basically, if I meet that condition, basically, if I have C1, C2, and C3 fit that, then I can make whatever vector I want. Or is that just going to give me 541? I think that's just going to be 541. But we can do something similar to get the full span here. So let me give myself a little more room. So let's do this now. Now we're looking for something a little more general. Except what's on the right of this is going to be A, B, and C. And hopefully these three parameters I'm dealing with will be, hopefully I'll be able to simplify them into maybe just one or two. All right, so how do we reduce? Do we need to guess, or can we rely on some stuff we've already done? I can definitely, I mean, I know how to reduce this matrix. I've already done it a couple of times. So let's just follow those steps again. The only thing we have to worry about now is what's on the right-hand side is no longer a fixed vector. It's this general thing we have to worry about. But we still have to modify it. So 2 row 3 plus row 2 to row 2 is the first thing we did. So 2 row 3 plus row 2 to row 2. And I'm not really even going to worry about, I'm looking at the wrong slide. Two row 3 plus row 2 to row 2. So what do I get in the left here? 1 4 2 0 3 3 1 2 0. All right, so how does this get altered? Should be A and C still. But then what's the middle? 2C plus B. Right? Then what do we do? Row 1 minus row 3 to row 3. A minus C. And then what did I do? No, I got both the rows to look like ones. So if I scale the middle row, or yeah, the second and third rows. All right, and then one more move was to cancel out a row. So row 2 minus row 3 back to row 3. And that was our last thing we did, right? What's 2/3 minus a half? A sixth. A 1/3 minus a half is, nope. Why did I subtract at all? 2/3 plus a half is 7/6. Oh, never mind. These don't combine at all. 1/3 B minus 1/2 C. All right, how we doing? So what? I don't think we can reduce anymore, or this is not. We didn't reduce any further than this, but what does this actually tell us? I think it can have solutions. Why would there not be solutions? Right. So you have a problem if you have 0, 0, 0, and then not 0, right? So what does that imply about this long string of terms? It has to be 0, otherwise we're stuck. So one thing we know for sure is that here's one condition: 7/6 plus 1/3 b minus 1/2 c equals 0. That's a lot of fractions, right? I hate that. Let's multiply the whole thing by 6. 7a plus 2b minus 3c equals 0. So that's definitely one condition. Are there others? The line above it says basically 2/3 a times c2. What is that true?
That's supposed to be 2/3 C.
Oh yeah. So how's that going to alter what I've already done? Or is it? Okay. So let's clean that up. Or did I make that further back? Nope. Right, row 2 plus row 3. So oh, that's why I was subtracting. 2/3 c minus 1/2 is 1/6 c plus 1/3 b minus 1/2 a. So then that final condition becomes c plus 2b minus 3a equals 0. So just multiply that whole bottom row by 6. So I think as long as A, B, and C fit this, we're going to be okay. Because if it is, then the bottom row of this matrix is just all zeros, right? Which means I have infinitely many solutions. I want some solutions. Any questions? All right. Okay, so now let's go a little bit of a different direction. So now I'm telling you, oh, what the heck? Now I'm giving you a span that a bunch of vectors has. Let's talk about what the vectors could be. So how might we approach that?
Big random number.
We can pick random numbers, but if there are infinite number of solutions, we'll be here a long time. Is there a way we can rewrite this? So this thing here in the square brackets, what's the order of that? 4 by 1. Yeah, it's not maybe not obvious at first glance, but that's a single column. But can we break it out? Can we like rewrite it in a way that might be more valuable to us? Because think about what the span really is. The span of a set of vectors is its combinations, right? It's linear combinations. So the span of S, like that generally looks like this: constant 1 times vector 1 plus constant 2 times vector 2, and then all the way up to constant n times vector n. The span that I have written for you here doesn't look anything like that. But could I rewrite what I have here as something that more resembles a linear combination of a few vectors? If so, how? What would stand in for the constants? What would stand in for the vectors? In this thing that I'm giving you inside the curly braces here, what are the constants? Yeah, x1, 2, and 3 are the constants. So what I would like to do is this: if I could write span of S as x1 times something plus x2 times something. So I have to do this for every single constant, but there are only 3 of them. So I have a way of figuring out what vectors could go there logically. Right. So we could, this is kind of like, I think we called this expanded vector format when we were parameterizing solutions in a previous chapter. So basically, which of these, so this right here is a 4-row by 1-column vector. Which columns involve x1? First and third. So row 2 and row 4 are 0. What should I put in for row 1 and row 3? No, they have x1s in them. So row 1 has a single x1. Row 3 has a single x1. What about for x2? What should that vector look like, top to bottom? 2, negative 1, negative 1, 1. And x3? 3, negative 1, 0, 1. So if that's what the span looks like, any linear combination, or so basically anything that looks like that, real number x1 times 1, 0, 1, 0, plus real number x2 times 2, negative 1, negative 1, 1, and so on. If that's what the span looks like, then what's the set of vectors that I am combining together? What do they look like? And how many are there? It's those 3 vectors. So, and again, let's remind ourselves of what the span of a set of vectors means. Now that we have all the pieces in place, now that I have the 3 vectors, think about what their span means. So if I wanted to find out everything that these 3 vectors span, then what I would want to do is just take any real number or any 3 real numbers, multiply these 3 things by those real numbers, add them together. Do that exhaustively for any combination of real numbers you can think of. And that's basically all condensed inside this set builder notation. So my vectors will look like x1 plus 2x2 plus 3x3 and so on, as long as x1, x2, and x3 are real. That essentially is the definition of a linear combination. So you basically have to like cull out the vectors that make up that set from the way that span is written. Any questions about the way all these things kind of work together? So a lot of different pieces. We're talking about what is S here? Like what kind of thing is S? I heard a span, I heard subspace. I don't think I can call it a subspace. Why is it not a subspace? Yeah, what's a subspace? And there are two criteria you have to hit for a pile of vectors to be a subspace. Closure by addition and closure by multiplication. Do I have either one of those here? I think at the very least, if I add the first two together, I get the third one, right? But what happens if I add these two together? I don't have anything with a 5 in the top row. So it's not closed. It has to be closed for every pair you can think of. So we're already done. It's not a subspace. But there is something I can call it. It's like something with way fewer restrictions than it's not even a vector space. Actually, it is a vector space. I'm sorry. Because if I add those things together or multiply them by numbers, they act the way you'd want. But S is a vector space. It's a set of vectors. It's just a collection of some vectors. How is that related? So how is that set related to its span? Like, how do I make that jump from S to span of S? Because the span of S, how many things are in S? Just those three things. How many things are in the span of S? How many is that? But what can x1, x2, and x3 be? Any real number. So that means there's an infinite number of things that are in the span. So the span is an uncountably infinite thing. But how do I make the span of S from S? Like, of what? It is. Because yeah, if I make x1, x2, and x3 all one, or actually, never mind. If I make x1 1 and x2 and x3 both 0, then I get the first vector, right? So I can select each one of my three vectors that way, but can also put 3 negative pi and e to the ninth here and get another vector in that span, right? So I can put whatever numbers I want in there. That's why the span will always we'll always have an infinite number of things in it. The set of vectors that make the span will almost always be finite. It can be infinite, but we won't really talk about those. But just by multiplying those vectors by constants and then adding those things together, you can make a lot of new things. So that's what the span essentially is. How are we doing? So I threw a lot of brand new like structural things at you this week. So if you're having trouble with them, I don't want to go too far without you. Please stop me. Okay, so I had a final question here. Can we reduce this? So I have three vectors that are spanning this set, or three vectors that I'm using to create the span. Do I need all three of them? Why don't I need all three of them? I sort of like hinted at it a little bit ago.
In your position.
So I think one of these is a linear combination of the others. So if I add this and this, I get that, right? So because of that, I think I could have another thing called T, which only has 1, 0, 1, 0, and 2, -1, -1, 1. And I will give you this. For right now, I will ask you to take this on faith, but hopefully you believe me. The span of S is equal to the span of T. Even though I took a vector away. Because this third vector in S, if I can add this vector to this vector and get that one, then I could take that out. That's already in the span of these two, right? Does that make sense? So basically anything that this is in the span of this and those three, like this is already doing all the lifting for that. So because vector 3 is a sum of vector 1 and vector 2, I don't need it. How are we doing? All right. So that brings me to the idea of linear independence. So a set of vectors is linearly independent if none of the vectors in the set is a linear combination of the others. So what we just saw was a counterexample. That set of 3 vectors was linearly dependent because I could make the third vector by combining the first two. So another way to think about this, let's say you have this long equation here, C1V1 plus C2V2, all the way up. Like basically if I add all, basically if I take all the linear combinations together and add them, I get the 0 vector. If the only way to do that is to have all the constants be equal to 0, then I have linear independence. That was kind of a strange way to think about it, but I want to kind of unpack it for you. So let's go back to the ones we just looked at. So let me take some things away here. Let's say this. I want to add some combination of these things together, and I want to get this 0, 0, 0, 0. So clearly this is always possible, right? If I just take the combination of 0 times everything, I'll always get the 0 vector, right? But is there a way to have non-zero numbers here and still get 0? The inverse of what? I can't invert a not square matrix. But I'll remind you that, remember the first two, if I add the first two vectors together, I get the third one. -1 times this plus -1 times this plus 1 times that. What does that give me? So the fact that I was able to come up with real numbers and not all of them were 0, that means I don't have linear independence. So if you have a linearly independent set, then if you have a combination that equals 0, the only way you can make that happen is if you scale them all down to 0. So let me give you a small one here. Here are 2 vectors that I will promise you are linearly independent. Is it possible to add some combination of these things together to get 0, 0? There's exactly one way to do that. Just make them both 0. But if I make this first one 1, there's nothing in this first row here to cancel out the 1 that I have. So you're stuck. So that's what linearly independent is. If I have basically 2 ways to think about it. I gave you the really rigorous mathematical formula way to look at it, and also the thing you can test is one of your vectors a combination of all the other ones. If it is, you don't have independence. So is this set linearly independent? make more room. No, 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 no. How can we answer that question? How can we find out if it's linearly independent? If you can add two of them together to get a third one, then you would definitely not have independence, right? Does anything like that jump out at you quite yet? But like, what if the combination is more complicated? What if it's 4 of the first one minus 3 of this one, and so on? Those are going to be a little harder to see. But is there a way I could find such a thing if it is out there?
All the matrix have zeros at the end.
Maybe. I'm not sure if I followed what you said. So like augment this 4x3 and put what to the right of it? The identity? All zeros? Oh, okay, interesting. Okay. So yes, that will work. But why will that work? Let's think about it. So what do the first, second, and third rows in these things all represent? Or maybe I should ask this: what does it mean for a set of vectors to be linearly independent? So I'm going to ask you to lean into the long form mathematical definition here. So if I take a linear combination, so basically if I take the first vector 1, -1, 1, multiply it by a constant, take constant 2 times 2, -1, -2, and so on. What should I set this equal to? 0, 0, 0, 0. And if this is linearly independent, what should I learn about C1, C2, C3, and C4? What should those constants be? All 0. So now let's set up this matrix essentially. So 1, 2, 0, -1, -1, -1, -1, -2, 1, -2, 2, 0 times C1, C2, C3, C4. But this is the equation I'm solving, right? What would this augmented matrix look like? So -1, 2, 0, -1, -1, -1, -1, -2. Does anybody have any suspicions about whether this is actually linearly independent? If it was linearly independent, what would I be able to do here? Go ahead. Well, I can already add up all the rows. So essentially we're solving a matrix equation here. If I were to solve this, like what would my goal augmented matrix look like? I guess it depends on the kind of reduction we do. So let's say we're going full Gauss-Jordan elimination. If we do full Gauss-Jordan elimination, what would this matrix look like ideally after we got done with it? Oh, wait, sorry. No, there's no last row. Okay, does this give you any suspicion about whether this is linearly independent? And then what would go here? A, B, and C? But if we have linear independence, then what should those be equal to?
Yeah.
Still zero. But then we would have x1 equals 0, x2 equals 0, x3 equals 0. What is that fourth column telling us? It can't be anything. It has to be, this has to be. So basically what this, let's kind of go backwards. Now that I've we've talked about what the augmented matrix would look like if we were able to complete Gauss-Jordan elimination. Then what's this spanning set of vectors? 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. If the thing we started with is linearly independent, then so is this. Then the opposite of that is also true. If the thing we started with is not linearly independent, then neither is anything we reduce it to. Is this thing that I wrote down here, is this linearly independent? Are you sure? What if I add, so if I multiply this by a constant, this by a constant, this by a constant, and this by a constant, and add those all together, I can get 0, right? Is there a way to get 0 if some of my constants are not 0? How so? C4 can be literally anything. C1, C2, and C3 have to be 0. It doesn't matter what C4 is. So let's try to generalize this a bit. I gave you, these vectors are of how many dimensions? So they're in R what? Oh, did I talk about this last time? When I have R with a subscript, it's R3. Okay. These are vectors with 3 components to them. But I have 4 vectors. Is there any way I could have gotten linear independence from that? I have too many vectors for not enough dimensions. So for right now, that's another thing I'm asking you to take on faith. But if you have 3 dimensions and I give you more than 3 vectors, one of them, at least one of them, is definitely a combination of the others. It has to be. Because here's your best case scenario, right? You told me that in a perfect world, you would be able to reduce this matrix to that. Even in that case, you have dependence. What does the not best case scenario look like? Well, it sort of looks like this. In that case, you really don't have independence. You have a 0 row as well. So either a full 0 row or a full 0 column gives you dependence. We okay with that? What about that? Is this at least possible? Right. So The big red flag I just told you about doesn't really apply here. I have vectors in R3. So now we can kind of set up the same thing. I would like to find out if I can multiply, if I can find a linear combination of these vectors that results in 0, 0, 0. Is the end goal any different? If I'm able to get to the identity matrix on the left and 0, 0, 0 on the right, then basically what you found is there's one way to get the zero vector, and it's if I have none of these, none of these, none of these. And if that's the only way to make that happen, then I have linear independence. So how can I start working toward that? Go ahead.
You can start by adding to
Two of row 3 to row 1. So that gives me 1, 8, 10, 0. I just thought of something. What's going to happen? What's going to happen to the right-hand side of this vertical line? Is anything ever going to happen to it? I'm not dealing with it then. So really the question is, can I invert this? Can I reduce this? So yeah, since you're dealing with the zero vector, it's never going to be altered. Because the things you're allowed to do are swap rows. Okay, you're trading zeros, or you're adding multiples of zeros to other zeros. You're not ever going to alter that last column, so we'll just ignore it. All right, what next? Excellent. Now we got the pivot. Let's make the things below the pivot 0, 1, 8, 10, 0, 7, 7, 2, 3, 7. All right, now what? R3 minus 2 row 1. Back to row 3. So 1, 8, 10, 0, 7, 7, 0, 3 minus 16. Yeah, minus 13. 7 minus 20, minus 13. Oh, I have concerns. I have concerns. Does anybody else have concerns? In what way? I agree with you. I just want to be specific for the good of the room. What's that? Row 3 will all go to 0 because why? Yep, they're linearly dependent because they're really the same thing. I mean, I can, so when I'm doing row operations, I can multiply any row I want by a non-zero number. So I didn't even write it down. I just multiplied the middle row by 1/7 and the bottom row by -1/13. Which means what? I have 1, 8, 10, 0, 1, 1, 0, 0, 0. So we know the answer is no. But the other question is, can we replace it with a set that is? So to do that, let's keep reducing. So let's be clear, what did I do to get there? Oh, I did row 2 minus row 3, back to row 3. So let's do full Gauss-Jordan elimination. What's the next thing I should do? Row 1 minus 8, row 2, back to row 1. So that gives me 1, 0, 2, 0, 1, 1, 0, 0, 0. Now what? I should be done, right? Okay. So now what have I learned? I've learned that basically x1 plus 2x3 is equal to 0. x2 plus x3 is equal to 0. So if I parameterize that, let's say that x3 is equal to t. Then what's x2 equal to? Negative t. And x1 is equal to negative 2t. So this right here basically gives us a list of constants. So basically, as long as x1, x2, and x3 satisfy all these requirements for the parameter t, then I found a linear combination that equals the 0 vector. So the answer is no. So let's look at an arbitrary one. Let's say that t is equal to 1. Then what do I know? I know that negative 2 times negative 3, negative 1, 2 minus 2, negative 1, 3 plus negative 4, negative 3, 7. Is that equal to 0? 6 minus 2 minus 4. Yeah, this should be 0. That's if we did everything correctly. So based on what we just found, it looks like somewhere one of these vectors has to be a combination of the other two. Doesn't matter which one. I think any one of them is a combination of the other two. So I think one way we could make this, at least maybe get this linearly independent, is to just remove one of them. We would still have to test and make sure that that is linearly independent, but clearly the 3 I gave you aren't. Because I can combine 2 of them to make the third one. How are we doing? All right, what else? Nothing else. All right, I think I know what happens. You can still see it, right? Christmas miracle. All right, so let's talk about briefly this idea of something called a basis, or plural bases. So I gave you these 4 vectors here. Does that span R3? So let's not worry about like really proving whether or not it does that. But from those 4 vectors there, could I use some combination of them to make every single vector I can think of that has 3 dimensions in it? So 41, negative 9, a billion? Could I make that using those 4 vectors? How? So 41 of these, -9 of these, a billion of those, and none of those? Okay, that works. But would we agree that I can make any 3-dimensional vector I want from these 4 vectors? So I would say yes, this subspace spans R3. Is it linearly independent? I see a shake of head. No. See other shakes of heads. Why not? You had the first 3, you get the 4th one, right? So I have a thing that spans the overall space I care about. They're not linearly independent. Do we have any suspicions about how I could make this thing linearly independent? A couple of you told me why it fails to be linearly independent. Why does it fail to be independent? What's that? You said a specific combination. If you add the first 2 together, you get the 4th one. So clearly the 4th one's a combination of the other 3. Is either one of those 3 a combination of the other 2? I don't think there's any way it's possible. They all have the wrong non-zero component. So now I would say this, having removed that 1, 1, 1 vector, this is now linearly independent. So 2 ideas here. Does it span a space you care about, and is it linearly independent? If you meet both those conditions, you have something called a basis. So if you have a set of vectors, so B is a smaller set of vectors, W is a larger set of vectors that's the span of B. So those are the 2 conditions here. Is it linearly independent? Does it span the larger space? If it is, then we say B is a basis of W. So yeah, more beefing up the vocab. In this context, this is what a basis is. So basically, it's a set of vectors that can generate the span. Questions on that? So every basis has a dimension. The dimension refers to how many vectors are in it. So what was the dimension of the basis we just talked about? So the thing I first gave you was not a basis, right? We whittled it down to something that is. What's the dimension of that basis? It's simply, it's just one number. It's how many vectors are in there. So the dimension is 3. So it's simply how many, not how many elements each vector has, or it is how many, or no, sorry. I don't want to get ahead of myself. It's not how many elements each vector has, it's how many vectors are in the basis. I am not going to get into this in 1 minute. So let's go ahead and hold off on this until tomorrow. And I'll see you then.